The air you just breathe in would once have been poison, not on another planet. Here, on this Earth, 3 billion years ago, oxygen was not life-giving. To most living things on this planet, it was lethal. For most of ancient Earth history, there was almost no free oxygen in the atmosphere at all. And life did not need it. Life feared it. To the organisms that dominated the prehistoric world, oxygen was a corrosive threat, more dangerous than any predator. Because predators had not yet arrived, then something began to produce it, quietly, relentlessly. And for much of the first life on Earth, that change became a catastrophe. So how did the molecule filling your lungs right now trigger one of the most devastating biological crises in the history of oxygen on Earth? How did something so small rewrite the atmosphere, the oceans, and the future of every living thing? And if one gas could transform the planet once, what makes you certain the air you depend on is as stable as it feels? This is the story almost no one tells about the prehistoric world. Not the age of ancient predators, not the reign of lost species. Before all of that, before eyes, before bones, before anything that could scream, there was a war, invisible, silent, and it shaped everything that would ever live. You are about to look at one of the most consequential turning points in natural history. A moment most people never learn about at all. The moment Earth's atmosphere became a weapon, and you're breathing the aftermath. You live at the bottom of an ocean of gas. Every second, that gas enters your lungs, feeds your blood, keeps your brain alive. You never think about it. You never question it. Oxygen is simply there, the most natural thing in the world. But here is one of the strangest facts most people never stop to consider. For the first half of Earth's existence, billions of years, the atmosphere contained almost none of it. The air was thick with methane, carbon dioxide, nitrogen, gases that would suffocate you in seconds. That was the normal state of the ancient world. Not blue skies, not breathable air, a chemically hostile haze that no modern animal could survive. And the life that existed in that world, the first life on Earth, did not want oxygen. It thrived without it. It was built to exist in a world where oxygen had no place. Then something appeared, something tiny, something that would become one of the most consequential forces in the history of ancient Earth. Not a meteor, not a volcano, a microbe. And what that microbe did over the next several hundred million years would alter the atmosphere, likely help freeze the planet and devastate more living things than any asteroid ever would. This is the story of how the air you breathe was born, and how its birth was among the most violent events the living world had ever faced. To understand what changed, you first need to understand what came before. For billion years ago, Earth looked nothing like it does today. There are no continents as we know them, no forests, no soil. The planet was a world of rock, lava, and water, and above it all hung an atmosphere that would kill any modern animal in minutes. The air was made of methane, ammonia, carbon dioxide, and water vapor. There was no free oxygen anywhere. Not in the sky, not dissolved in the ocean, not in the rock. Zero. And yet, life existed. Deep in the oceans, around cracks in the seafloor where heat and chemicals poured from below, the first organisms had already appeared. They were not plants. They were not animals. They were something far simpler. Single cells, microscopic, fragile, but they were alive. These organisms, called anaerobes, survived by feeding on chemicals. Iron, sulfur, hydrogen. They pulled energy from the raw geology of the planet itself. They did not need sunlight. They did not need oxygen. In fact, oxygen would have destroyed them. To understand why, you need to understand what oxygen actually does. We think of oxygen as gentle, life-giving, the good gas. But oxygen is chemically one of the most reactive elements on Earth. It pulls electrons from other molecules. It breaks chemical bonds apart. When iron is exposed to oxygen, it rusts. When wood is exposed to oxygen and heat, it burns. That is not coincidence. That is oxygen doing what oxygen does, disrupting molecular structures. Fire is oxygen. Rust is oxygen. Decay is oxygen. Now imagine a living cell with no defense against that. No enzymes to neutralize it. No biological shield. A cell built for a world where oxygen simply did not exist. Introduce oxygen to that cell, and the chemistry begins to fail. The membranes buckle. Internal structures break down. The cell dies. That is what oxygen was to the earliest life on this planet. Not a gift, a poison, a molecular agent that nothing alive was equipped to handle. And for roughly 2 billion years, that did not matter, because there was no free oxygen to worry about. Earth was a stable, ancient world, dark, quiet, chemically predictable. The organisms that lived in it had no enemies, no competition, no predators. Life was simple, microscopic, and everywhere. Then, around 2.7 billion years ago, something new appeared in the shallow waters. Something that could do what nothing else on Earth had ever done. It could eat sunlight. Cyanobacteria. They were still tiny, still single-celled, still simple. But inside them, a new chemical process had evolved. One that would become arguably the most consequential biological innovation in natural history. Photosynthesis. They absorbed sunlight. They absorbed water. They absorbed carbon dioxide. And as a byproduct, something they did not need and could not use, they released oxygen. At first, it did not matter. The oxygen they released was immediately absorbed. It reacted with dissolved iron in the oceans. It bonded with minerals in the rock. It disappeared as fast as it appeared. The planet had enormous chemical capacity to absorb free oxygen before it could accumulate. But the cyanobacteria did not stop. They kept multiplying, kept spreading, kept producing. And slowly, over hundreds of millions of years, that capacity began to fill. The iron ran out. The minerals saturated. And for the first time in Earth's history, free oxygen began to accumulate in the atmosphere. The planet had never experienced anything like it. And what came next would not be kind. What happened next is one of the most severe biological crises in the entire history of life on Earth. Scientists call it the Great Oxidation Event. But that name is too clean, too polite. A better name, one some researchers use, is the oxygen catastrophe. Around 2.4 billion years ago, free oxygen levels in the atmosphere crossed a critical threshold. Not by much. Even at its peak, oxygen likely reached only a small fraction of today's levels. But the geological and chemical evidence is clear. Something shifted. And to the organisms that had dominated this planet for over 1 billion years, even a trace of free oxygen was devastating. Imagine an entire biosphere. Billions of organisms, spread across every ocean, every shallow sea, every thermal vent and tidal pool, a global community of microscopic life, stretching back almost to the birth of the planet itself. Now imagine a slow, invisible poison spreading through their world. A gas they cannot see, cannot flee, and cannot fight. That is what oxygen did. The anaerobic organisms, the ones that had thrived in a world without oxygen, began to die. Not in a single dramatic extinction, like an asteroid impact. This was slower, more systematic, more thorough. Over time, fewer and fewer environments remained where oxygen could not reach. The organisms that could not tolerate it were pushed to the margins, to the most extreme, most isolated pockets on the planet. Deep sea vents, underground sediments, places where oxygen still struggled to penetrate. Some of those organisms still exist today, living fossils, remnants of a world that oxygen erased. You can find them in oxygen-free mud at the bottom of swamps, in the guts of animals, in hot springs where the chemistry still resembles the ancient Earth. They are refugees, billions of years old, hiding from the air itself. But the oxygen catastrophe did not stop at reshaping the microbial world. It may have changed the climate. Methane, the greenhouse gas that had helped keep early Earth warm, reacts with oxygen. As oxygen levels rose, methane began to break down. And methane had been among the key factors holding back the cold of space. Many researchers believe what followed was one of the most extreme climate events in Earth's history. Temperatures dropped sharply. Ice spread from the poles toward the tropics. At its most severe, if current leading hypotheses are correct, large portions of the planet, possibly including equatorial regions, may have been covered in ice. A state geologists call snowball Earth. The details remain debated. Some researchers favor a less total freeze, a slushball Earth with open water near the equator. But what the geological record makes clear is that the cooling was severe, prolonged, and global in scale. Sunlight bounced off ice back into space, deepening the cold. A feedback loop that proved very difficult to break. One microbe's waste product may have helped freeze a planet. The cyanobacteria did not intend to do this. They had no intent at all. They were just cells, doing what their chemistry told them to do. Absorbing sunlight, releasing oxygen. And that single, mindless chemical process drove one of the most severe crises life had yet faced on Earth. We know what happened. The deeper question is how anything survived it. How did life persist through a global poisoning, a possible global freeze, and come out the other side? And more importantly, how did life eventually learn to use the very thing that almost killed it? That answer is the key to understanding everything that came after. Every prehistoric creature that ever walked or swam or flew. Every extinct species. Every living thing you have ever seen. All of it traces back to what happened next. If this kind of deep time history is why you are here, you already know what to do. Because from this point, the story only gets stranger. Here is the part of this story that should unsettle you the most. Life did not merely survive the oxygen catastrophe. It adapted. And what it adapted in, it changed the planet forever. To understand how, you need to understand a simple truth about evolution. It is not planned. It is not design. It stumbles. Randomly. Blindly. Millions of mutations happening constantly. Most of them useless. Most of them harmful. But every once in a while, by pure chance, a mutation lands somewhere useful. And in a world now filling with toxic oxygen, one class of mutations was more valuable than any other. The same chemistry that made oxygen lethal also made it powerful. It was highly reactive, which meant that if a cell could control that reaction instead of being destroyed by it, the economics of life could change entirely. Some cells, through random genetic accidents, developed proteins that could neutralize oxygen. Instead of letting it tear their chemistry apart, these proteins captured it, contained it, and then something remarkable followed. They used it. Oxygen, it turned out, was an extraordinary fuel. When harnessed correctly, oxygen-based metabolism produced far more energy than any chemical process that came before it. Enough to change the scale and complexity of life itself. The cells that could breathe oxygen did not just survive. They thrived. They outcompete everything around them. They grew faster, reproduced faster. They had access to an energy source that nothing else could touch. The poison became the advantage. The weapon became the fuel. And this single adaptation is the reason you are alive. Nearly every complex animal on Earth today depends on oxygen for energy. Every insect, every fish, every mammal, including you, your mitochondria, the tiny structures inside your cells that produce energy, are the direct descendants of this ancient shift. Most biologists believe mitochondria were once free-living bacteria, oxygen-breathing bacteria that were engulfed by larger cells. And instead of being digested, they formed a partnership. The larger cell provided protection. The smaller cell provided energy. Enormous amounts of energy, powered by oxygen. That partnership, that ancient merger, is what made complex life possible. Without it, there would be no animals, no plants, no fungi, no eyes, no brains, no bones. Every prehistoric creature that ever existed, every ancient predator, every lost species, every extinct animal owed its existence to this moment, to cells learning how to use the thing that once would have killed them. But here's what makes this story stranger still. That transition from a world without oxygen to a world built on it, was not smooth. It was not clean. It did not happen once and settle into stability. Oxygen levels on Earth have fallen and surged many times since the Great Oxidation Event. And each time they shifted dramatically, life paid the price. The Permian extinction, the worst mass die-off in Earth's history, far larger in scale than the asteroid that killed the dinosaurs, unfolded alongside severe disruptions in atmospheric and oceanic chemistry, likely including major oxygen stress. 90% of all species on Earth vanished. The ocean floor became a graveyard. The land fell nearly silent. Oxygen giveth, and oxygen taketh away. The molecule is not your friend. It is not benevolent. It is a reactive, volatile chemical that happens by accident, by chance, by the blind mechanics of evolution, to be something your cells can exploit. Right now, Earth's atmosphere is approximately 21% oxygen. That number is not random, and it is not safe in the way you think it is. At significantly lower oxygen concentrations, human cognition and survival deteriorate quickly. The precise thresholds vary. Altitude, duration, individual health all play a role. But the margin for error is narrower than most people imagine. At significantly higher concentrations, something else becomes a problem. Wildfire behavior changes radically. Vegetation ignites more easily. Fires spread faster, burn hotter, and become far harder to contain. The planet becomes a much more combustible place. 21% sits in a narrow range where complex life can function, and nothing is maintaining it on purpose. There is no thermostat, no design control. What holds oxygen at this level is a web of biological and geological processes. Photosynthesis, respiration, decomposition, ocean chemistry, volcanic emissions, rock weathering, all interconnected in ways no scientist fully maps in isolation. These processes have kept oxygen roughly stable for the last several hundred million years. Roughly. But the geological record tells a more turbulent story about the deeper past. In the Carboniferous period, around 300 million years ago, oxygen levels climbed significantly higher than today, possibly toward 35%. The consequences were visible in the fossil record. Insects grew to extraordinary sizes. Dragonflies with wingspans wider than a hawk. Millipedes longer than a car. Life responded to the energy-rich air by scaling up in ways that seem almost impossible now. Then oxygen dropped, and those giants disappeared. Every one of them. Extinct species that could never return because the atmospheric conditions that enabled them were gone. Again and again in Earth's history, major shifts in atmospheric oxygen have forced life to adapt, migrate, or disappear. The pattern is not subtle. It is written in the rock. And today, right now, we are running an experiment with no clean precedent in this record. We are burning fossil fuels, the buried remains of ancient carbon, and releasing the combustion products into the atmosphere faster than any natural volcanic episode in the geological record. We are altering ocean chemistry. We are removing the forests that produce oxygen and cycle carbon dioxide. The parallel to the cyanobacteria is not exact. They transform the atmosphere over immense stretches of geological time. We are changing it within centuries. But the deeper pattern is the same. Life can alter the chemistry of the air in ways life itself may not survive unchanged. Here is the truth this story has been building toward. The air you breathe is not permanent. It is not guaranteed. It is not a birthright. It is an accident, a temporary chemical arrangement held in place by forces that have shifted before and can shift again. For 2 billion years, Earth had no breathable atmosphere. Then a microbe changed everything, and in doing so, triggered one of the most severe crises life had yet faced. The survivors adapted. They turned poison into power. And over billions of years, they built the world you see around you. Every breath you take connects you to that moment, to the cyanobacteria that produced the first free oxygen, to the cells that found a way to survive it, to the ancient catastrophe that made everything possible. You are not separate from the story. You're the latest chapter in it, and the chapter is not over. The atmosphere is changing again, not as slowly as before. The question is no longer whether the air can shift. The question is whether what lives in it can adapt fast enough this time. The cyanobacteria had billions of years. You do not. What you have just watched is one chapter in a much larger story. The story of how ancient world secrets, buried in rock, frozen in chemistry, written in the genes of every living thing, still shape your world today. But there is another chapter, one that comes after the oxygen catastrophe, after the ice melted, after the world began again. Something appeared in the oceans, something that had never existed before. The first creatures with bodies, with eyes, with jaws. They arrived in an explosion of life so sudden, so violent, so unexplained, that scientists still argue about what caused it. Some say it was oxygen that unlocked it. Others argue something else happened, something stranger, something the fossil record still cannot fully explain. We will go there next. If this video changed how you see the air around you, leave a comment with what disturbed you most. Every comment tells us you want to go deeper, and we always go deeper.